So as we mentioned, as everyone knows from the registration, it's a discussion today about PERC versus TOPCon cell technology. Here's an overview of this presentation. So first, we'll start off with the intro, the basics of solar cells. So when we talk about PERC and TOPCon, they are solar cells. So let's have a quick refresher and bring up to speed what exactly is a solar cell to better arm yourselves to delve into these topics of PERC and TOPCon respectively. Then I will also go into detail about what is PERC and what is TOPCon, chapters 2 and 3. And we'll discuss the differences, why you would pick one over the other. What is the technical difference? What is the atomic structure and layout difference? What is the performance and financial implications, etc. And then I'll also give you examples of what we have deployed in terms of our own cell technologies with respect to these, and a Q&A at the end. So, intro, basics of solar cells. Let's begin here first. What is a solar cell? Well, as a quick definition, it's an atomically modified semiconductor that can generate electric current, DC, from incident photons. We all know this, hence the name renewable energy, infinite amount of photons from the sun. And then, basically, we have a cell here. I've given you a typical example. In today's age, it's about 182 by 182 millimeter by 0.14 millimeter thickness. So that's about 140 micrometers. So it is a very thin, very fragile, cell substrate. And as you see here, I've also grouped all the input raw materials. So obviously the semiconductor is the main material. In modern solar history and current modern crystalline solar cells, we are using silicon semiconductor because it is abundant, it is stable properties, and it is easy to modify. So as you can see in this first diagram, it's sourced from the ground as a silica sand, SiO2, and other compounds of it. Then it is purified to crystalline, then form ingot with industrial processes, namely the Swarovski process, into monocrystalline. And then it's sliced very thin to form the wafer. This is the blank canvas where solar cells begin their life, before other techniques are applied to make it into all these different cell technologies we hear today. So how does it work? It works on the P-N junction principle, which is the basis of solar cells and other technologies like LED lights, etc. So P&N represents P-type semiconductor and N-type semiconductor, respectively. The P-N junction has these two types of semiconductors. The P-type represents positively charged carriers, hence the P. So it is doped with an impurity or element called boron or gallium, and these are known as acceptor atoms. Acceptor because they have 3 electrons in the valence band compared to silicon, which is 4. Apologies, one more joining. So basically, silicon, let's start with silicon. It has 4 electrons in the valence band, and therefore it connects with 4 others, has 4 covalent bonds with neighboring silicon atoms. Think of it as like a crystal lattice structure. When you dope silicon with boron or gallium, which is now we learned an acceptor atom because it has 3 electrons, which is 1 less than silicon, it has a vacancy for an electron. So we call this vacancy a hole, which is positively charged carrier. And then in the N-type is the opposite. So it has impurity. The dopant is phosphorus, being the agent, phosphorus. If you look, this one has 5 electrons in the valence band. So this is 1 extra than silicon, and therefore it has a donor. It's a donor atom, has 1 extra electron. So naturally, it's negatively charged carrier. Therefore, hence the name N-type. So when you connect these two together and form this barrier, it creates a p-n junction. Now this creates an electric field caused by the depletion region, which has an imbalance of a charge flow, and hence electrons can drift to the external circuit. And this is the current flow we recognize as electricity generation. I mean, the previous example was the basics, but this is more realistic view or cross-section view of a solar cell. So you have obviously the N-type substrate. which is in this case the base. So when we talk N-type, P-type panels, we're talking about the base substrate, because every cell has to have both P and N, because that's how the solar cell or photovoltaic principle works. But if we talk the certain cell, N-type or P-type, we're talking about the base substrate, which is the thick layer of the silicon cell. Then, of course, in here you can see we have the P-type towards the top, the front of the cell. Then it has the other layers necessary for the solar cell, which is anti-reflective coatings, the front electrodes or bus bars, as you hear, the rear bus bars, and towards the bottom or the rear, there is also some more passivation layer, which is additional to the N-type. I'll go into further detail later for that. So evolution, right? So what's been going on and what's going on today? In recent modern history in the last, I guess, decade and a half, we started with smaller cells, 156 millimeter, and they've progressively increased in size as the ingot manufacturers or polysilicon manufacturers are able to manufacture at a larger diameter of ingots. So currently we're sitting at 182 millimeter, which is the mainstream square cell format size. And this is pretty obvious from many publications and also just by looking at the market. And we also have M12 currently available at a smaller share. So this is where we stand. As you can see, in the 90s, we had as small as 125 millimeter, and slowly, not only the cell size increases, but other features of the cell change, such as the amount of bus bars increased, the shape of the cell, how we configure the cell, such as full or half cut or even triple cut these days, as you can see in some limited models from some brands. So yeah, the half cell is the more mainstream current configuration because of its enhanced benefits, such as lower operating current to be more compatible with MLPE and inverter power conversion equipment, as well as reducing power losses for any disturbance to the cell to minimize loss on the whole module. As you know, the power and current relationship is proportional to the square. So if you halve the current, it will be 4 times less affected. Here's a snapshot of the cell technology and efficiency last 10 years. So, sorry, I just want to make sure you can see the bottom. Well, anyway, from 2004 to 2012, we see the cell technology was called aluminium back surface field. I will show you the schematic for this one. As time went on, we had increasing technology efficiencies and different styles. So we see there was PERC, which is the mainstream today, back passivation. Then we had more advanced manufacturing techniques to optimize it. So you see the super PERC. And now, currently, we're in this stage today, which is N-type TOPCon. And it has a boost in cell efficiency. So this is the modern cell technology portfolio. You see historically dominated by back surface field, more recently monocrystalline. Obviously multicrystalline is now phased out, and it was dominated by PERC for last 10 years. And now we slowly see the domination of TOPCon increase through both TOPCon and HJT, but mainly TOPCon at the moment. Then we also see to the future some other techniques such as back contact style cells, which means no front bus bars to minimize shading on the front, and also tandem. Tandem represents multiple PN junctions like we saw in the previous slides. So this is an overview of the mainstream cell technology adoptions from all the current major brands. As you can see, it's mainly HJT, TOPCon, and back contact cells. As you can see, everyone is favoring the TOPCon because it makes the most economical sense and also high efficiency. This is some literature from ITRPV and InfoLink to further demonstrate the current market share of the technologies. You see in the orange here, PERC is dominating from this year and many previous years. However, the gray represents the TOPCon, which is coming more and more proven to be more popular. As you can see, in the next 5 years, it will be overtaking PERC. In 10 years, it will be about 70% market share. And here is another graphic here to represent the efficiency of all the different techs. So you can see this square one is an outlier, it's pretty high, but this one represents the tandem, which is far reach from commercialization of market adoption because of the high costs to manufacturer and also the complicated process accordingly. So this is out of reach at the moment. But the second best, you can see it's shared among like two or three different cell technologies, namely the HJT and TOPCon. So that's what's going on today. Now, what you've come here for, what is PERC solar cells? So this is a schematic of the PERC solar cell. Basically, it stands for the acronym, so you never forget, passivated emitter rear contact. The name of this cell is based on what they've been doing, what they're doing on the rear of the cell. The focus is here at the rear. Basically, everything else about the solar cell is what we've learned so far. It has a P-type substrate, namely most PERCs are P-type, by the way. So it has a P-type base layer, obviously the N-type at the top, a thin layer. Then obviously the common ARC coatings that you see on all cells, front and rear. However, they've intelligently printed these back electrodes in this formation to not only allow rear side photon incidence, but also minimize the amount of passivation needed. So passivation basically means it wants to increase the amount of charge carriers in this region. Why you want to do that? Because the more charge carriers you have, the more chance they will be consumed and drifted to create current. So therefore, in a P-type, we see the substrate is P-type. We learned before it's doped with boron or other elements with the same valence electrons, which is 3. In this case, you see aluminium, which also has a valence electron count of 3. And if you strategically dope it in these regions near the electrodes, which is all we care about because this is where the current is being collected and flown through, then you're able to optimize the cell in terms of optics. So optics meaning its optical efficiency, so you can gain more photons from the rear and not be lost. And from a recombination perspective. And recombination just basically means the charge carriers, positive and negative, electron and hole, recombine and stabilize back to their normal state with no charge. We don't want this. We want to maximize the amount of free carriers flowing to maximize the current. So this is what passivation achieves. And this is how the PERC solar cell was based on these two principles to optimize. The previous technology that the PERC is based on is very similar. It is basically the PERC. So if I just quickly go here, because I'm not sure it's visible on your screen, but the PERC was based on aluminium back surface field, which is here. It's the same thing, but the whole rear side is covered with aluminium. So you cannot even achieve any photons to be captured from the rear. And at the same time, if you have too much passivation, then also it has some negative benefits as well, which means if you have too much doping in that region, then it can also cause too much resistance. So this is another reason why in PERC it's more efficient, because it's like strategically or selectively located doping. So now we're on the topic of PERC. I want to share with you a cool story. Basically, PERC, it dates way back to the 80s. It was actually invented by the PV R&D team, research team from UNSW, led by Professor Martin Green. They invented this in the 1984, and it broke multiple cell efficiency records. So it was recognized by the NREL, it was recognized by all the major institutions. So Australia really put photovoltaics on the map. And you can say Australia invented Wi-Fi, but we also invented PERC. So this is also something we should be proud of as Aussies. And the story is, it was invented by Professor Martin Green's team. And also, I'd like to mention Suntech's founder, Dr. Shi, was a Sydney citizen studying at UNSW under Martin Green. So he took a lot of technical expertise from this team, and he graduated obviously as PhD graduate and founded Suntech accordingly from his technical knowledge he gained in 2001. So from there, he was able to optimize the manufacturing. And yeah, Suntech was #1 in terms of volume capacity, as you see here in this graph, market share, for 12 years from the inception of establishment to around 2012, 2013. And they used a Pearl solar cell technology in their early modules here. You can see the name Pluto cells. This was very famous in the early days, just like the likes of BP Solar when they had their modules. So yeah, this is the history. And basically these cells adopted this Australian technology. Here's a quick overview of the process to manufacture the cell from its blank canvas, the wafer, all the way to a solar cell, which is what we see in the panel, in the module. So as you can see, there's a multiple processes, texturing, which provides like kind of a texture on the cell to maximize the optical losses. If you have pyramids, you're able to capture light better instead of just it simply reflecting off a straight surface. Then you have other processes to optimize this cleaning. Then you have the implantation of dopants. Like I mentioned, you have to modify the silicon. It cannot be in its raw intrinsic form. It has to be extrinsic. They do this with these chemical processes. They fire via a chemical vapor deposition process. So they do either phosphorus for the N-type and boron for the P-type. And yeah, they also put the formation of anti-reflective coating, then also the electrodes. These days, it's wires, so they optimize the surface area, and they optimize the shape of the electrode to maximize optics once again. Before, it was those ugly, thick ribbons you see in the previous old school panels. But this obviously had its drawbacks. So currently we use silver paste and wires to create the electrodes, namely the bus bars, and you also sort of see fingers, which is printed in adjacent to the bus bars. So this is PERC, and TOPCon is actually really advantageous because it uses very similar production line. It only has to add 2 to 3 extra steps, which I'll go into detail what they are for next, to create the TOPCon cells. Just checking, anybody in the lobby? Okay. So now let's go back to what is the TOPCon. Chapter 3. So TOPCon basically stands for tunnel oxide passivation contact. Once again, let's think of it as what we've been learning so far. You have a substrate, which is the base thick layer of the semiconductor. In TOPCon's case, it's N-type. Then you have the P-type layer at the front, which is the thinner layer. In this case, it's P-type, denoted by the P you see here. Then obviously you have your passivation and your anti-reflective coating. So TOPCon has aluminium passivation, which is the dopant for P-type. So aluminium or boron or gallium. Then you have SiNX. So this is silicon nitride as one form of its compound. This is used for anti-reflective coating. Obviously, the silver bus bars, as we already learned, for the electrodes, metal contacts. The difference here is really at the bottom once again. So we have a thin, very thin, in the vicinity of around 1 to 2 nanometers thick of a silicon oxide or dioxide layer. This basically allows the less recombination of the electrons and hole pairs. Then another layer of polysilicon. Now you may be wondering, this is really odd. Why polysilicon? We've been doing mainly other compounds like monocrystalline and all these things. So polysilicon here is also supposed to help the conduction of these charge carriers. And then they have obviously the anti-reflective coating at the rear. So this is the main difference. And the advantage over PERC. Namely, there is 5 key ones I want to mention. First one is the higher efficiency. So because of this optimized rear side with the thin silicon oxide and polysilicon layer, it's able to boost the efficiency to a theoretical upper limit of 28.7%. So that's substantially better than PERC's theoretical cell efficiency limit of 25. and HJTs of 27.5%. Another thing is you may be already aware the lower degradation rate. You can see this obviously from the first page of the data sheet. It has better figures for the degradation in the first years and consequent years, therefore able to provide you better warranty. So this is thanks to a lower susceptibility to LID, which is light-induced degradation, and LETID, which is light and elevated temperature-induced degradation. Furthermore, it is better prone to temperature, so it has a better temperature coefficient, so it loses less power per degree Celsius above 25. This is what basically it's saying. So in plain English, it operates at a lower temperature. You can just say this, right? And lower temperature means higher efficiency because less thermal loss. Another thing is high bifaciality factor. So the whole rear side is covered with passivation and tunnel oxide for the silicon oxide tunnel layer. This also helps dramatically with getting not only minimizing recombination, but also having that rear side available for photon incidents. And low light performance is also enhanced. So periods of cloudy overcast weather, or just simply in the early morning and evening periods of the solar curve, it will be boosted with TOPCon. So again, with numbers, these are the key differences in terms of efficiency, the yield, the mass production difficulty, and compatibility, capacity, etc. So we mentioned lower temperature coefficient. What is it? So namely, for TOPCon, you're seeing around minus 0.3% on average, and PERC is about minus 0.34%. So you can see here at really elevated temperatures as we go in, especially in the spring, summer months, when you see these temperatures around 60, 70 degrees, then you can see about 2 to 3% gain in nominal capacity retention. Lower working temperature as well. So like I mentioned, because of the temperature coefficient. So here are some real life data analysis comparing the TOPCon and PERC module, and it analyzes it throughout the day in the first graphic here. PERC is in the yellow and TOPCon's in the gray, and the irradiance is the blue. So you see throughout the day, the ambient temperature is the orange, and the gray curve is always has a delta below the yellow. Same thing here, TOPCon blue, PERC orange, slightly below at all times. And this is on a monthly basis here. So lower irradiance performance boost. As I said, excellent low light performance throughout the day. And if you have overcast days, then this is where the benefits really are reaped. And it's about, yeah, depending on the irradiance levels, you can see here a gain of 0.7% under different irradiance conditions. Performance guarantee. So here's a graphic of this in motion. We have typically these days 25 years or 30 years power warranty or performance warranty. And it entails basically a guarantee from manufacturer each year. How much can you retain of your nominal capacity? So for TOPCon, it drops only 1% in the first year compared to PERC, which is around 2%. Then every subsequent year after that, it only drops 0.4% compared to PERC's 0.5 or 0.6. So yeah, it's energy yield retention is very good. More reliable weather resistance. So also they are able to have greater resistance to weather as per our internal testing and from third parties. Done a range of tests such as thermal cycling, damp heating, dynamic testing, PID, etc. You can see it's well and truly below the 5% degradation buffer or limit threshold from the IEC standard. And here is the respective performance. It's worth mentioning, yeah, Suntech's modules also 5 consecutive years of reliable performance from PVL or PEVL, however you want to say it. Rear side photon capture is better, like I mentioned. So On the data sheet, this is represented by its higher bifaciality factor of 85% roughly, which is about 10% higher than PERC products. And you can see here in this graphic, power generation gain is you can see here it's benefited most days here. So yeah, you see a gain here about 0.8 all the way to 1.65. For this singular aspect, it's pretty good, right? Now, this is a summary of all the things we explored, the advantages of TOPCon, summarized into one here. So we've got different contributions of gain, LID improvement, bifacial improvement, temp coefficient, working temp, low light, respectively. Overall, we see a benefit of around 3.74%. Of course, this is based on a specific test, specific condition. Every system is different. It must be on a case-by-case basis. But here it's just, again, proving 3.74% extra energy yield. Multiply it by your cumulative energy yield. You can try to calculate, how much extra revenue it can bring to your plant and whether it's worthwhile the capital increase over PERC, especially in the long term. And here is field data that Suntech conducted a test on smaller array size. This is 3-string layout of 18 pieces per string. And you can see a monthly analysis of its generating capacity in terms of specific yield, so kilowatt hour per kilowatt peak. And you can see it's ranging from 3% to 4.5% to 5% here. So it is really a substantial gain. So what is some of Suntech's deployed cell technology? What have we been doing? So this is like a portfolio overview of our products. So you see we adopt PERC for many, many years and still do to this day via our Ultra X and Ultra V products. So you can see in the Ultra X, it adopts the largest current cell format available today, which is 210. And Ultra V is adopting 182 square format. So these are the range of different models represented here by the PICs and associated power class. Currently, our mainstream that we like to push to our customers now is also TOPCon, obviously, because of the benefits we just went through. We have it in the square 182mm format, and also the rectangular is a new product coming soon. So I thought I'd mention this in today's presentation. And these are the associated power classes. So you see the smaller ones for domestic rooftops and some commercial C&I rooftop projects distribution. Then we see some of our utility application modules, such as this one here, and this one ranging from 585 all the way to 635. And then we also have another new range, which is the Ultra X Pro. So it's the same as the first one here, but with the TOPCon technology. So 210mm square cell with TOPCon cell. And in this format of the Ultra X, it can go up to 700 watts with 22.5% efficiency. So this is a major power class. What are we doing with TOPCon in terms of our capacity and production? So we began mass production in 2021 in our Wuxi 2 gigawatt digital factory. And currently we produce around 17 gigawatts of cells throughout our 4 plants. So with further growth plans as well. So we're heavily invested in this new technology and we are ready already with large capacity. Of course, I want to mention another important information here is this raw material that I mentioned at the very beginning, such as semiconductors, such as metals, and all the other associated materials for modules. Always we have to be ethically sourced. So Suntech is very transparent, publishes a lot of literature to, disclose our policies and regulations to mitigate any sort of modern slavery or supply chain risk. And we also disclose our suppliers. So we are very transparent this way and think we comply to a very good degree. And that's pretty much it, guys. Thank you for your attention and for your patience throughout the presentation. Any questions, please feel free to ask.
Yes, Ramsey, just a quick question in regards to the warranty for the TOPCon PV modules. Is it 15 years or 25?
So we want to be specific with the models because there is differences between the residential domestic ones and the utility. So if we're talking TOPCon PV modules, we have our residential Ultra V Pro minis, which is ranging around 440 watts. These ones are 2525 or 2530 for the bifacial double glass model. When we're talking about the utility products, which I'll go back to show you. So yeah, the one I just mentioned, 440, is this one. Ultra V Pro Mini in this format is 2525 or 2530. The utility, which is these two, will be 15 years product and 30 years performance warranty.
Thanks, Ramsey. It's Paul here. Yeah, good presentation, good info. Thank you. My question relates to cost, CapEx. You sort of touched on that, the TOPCon may be higher CapEx, but I just wondered if you're able to, you know, put some stats or percentages around that. What's the delta?
Good question, Paul. So definitely this is a big consideration, any projects, you know, ROI or COE. So short answer is I can't give an exact figure, but I would say in the realm of about 0.5 cent or maybe 1 cent per watt. It really depends on, of course, what's the current scenario in the upstream supply chain in terms of raw materials, volume, things like that. But I would say on average about half a cent per watt.
Okay, thank you. That's okay. I mean, when we're talking cents per watt, broader question, it's quite low at the moment. Where do we go from here? Is it going to reduce further? Or
Yeah.
it's not sustainable? I'm just not sure. As you get more efficient, maybe there is some more improvement in cost that may be realized.
Yes, a good question again. So at the moment, the current scenario is PERC is still having the larger market share. However, this is rapidly shifting, as you saw in the previous graphic at the top, beginning of this PPT. TOPCon is really not far behind and very closely catching up. So two things here. One is once the manufacturers all adopting TOPCon, which they will be doing very shortly, then there will be a natural economy of scale, and I think that will drive the price down. Secondly is PERC has already reached the threshold of its max theoretical cell efficiency. So not only is it not getting more popular, it's not getting more efficient. So that will further drive the phase out. But TOPCon, however, there is still headroom to increase the cell efficiency as everyone's manufacturing process is optimized. So to make TOPCon, there is like actually 3 or 4 ways, different ways to make it. So throughout these 3 methods, you know, one or the other could be improving over the next few years, and therefore that could drive the efficiency higher and higher, like I mentioned, to reach that max theoretical limit of around 28% cell efficiency for TOPCon. So basically, there is growth for TOPCon available, and that's also why I think the price will drop. I hope that kind of answers your question.
That's a good answer. Thanks, Ramsey.
Yeah, you're welcome, Paul. Yeah, as I said, guys, I tried to just do a high-level discussion. I didn't want to get into too much R&D or technical detail, but yeah, please let me know if you have any other questions. I hope you took something from it today.
Hi, Ramsey. Yeah, I do have another question. I don't know if you can answer it, though. It's regarding manufacturing and acceptance criteria in the different tests, like routine and type test. Is there any, any test that has been added that is specific to TOPCon, or are the acceptance criteria between the two cell technologies, is that changing at all?
It's a very good question, actually, and I'm not sure if I have all the answers, but I can say in terms of the new quality control, quality assurance testing requirements, I don't think there has been any additions in terms of different types of tests. They all, stem from the IEC standard test requirements that you see in some of the slides, like thermal cycling, PID, LID testing, mechanical dynamic loading, all these things. However, I think from most manufacturers, as they provide their TOPCon module samples to these institutions, they're seeing obviously the higher performance of many things, PID, performance, LID, etc. So this is what's being highly regarded in terms of its TOPCon. But I will take your question back to technical head office and see if they do have any other sort of quality assurance type testing. But as I know, it's still the same.
Okay, Ramsey, thanks. Maybe I will be able to drop by your stand in All Energy and maybe ask someone from your team that's
Yeah,
that handles manufacturing. Thank
yeah,
you.
yeah, absolutely. Feel free to visit, please. We're very excited. Have a nice big booth, so there's plenty of room for all of you to come. And yeah, grab a coffee, whatever you like, water. We look forward to it.